Welcome to a video on isosceles right triangles, sometimes called 45, 45, 90. In the diagram, we have an isosceles right triangle. Notice the two legs are labeled as X, meaning they're identical. So we could conclude that the two angles are 45 degrees. And there's where it gets a secondary name. We have a 45, 45, 90. So since it's a right triangle, it will behave according to the Pythagorean theorem that we discussed in previous videos. If we plug in the appropriate labels that we have on the legs here, we'll get that x squared plus x squared is equal to the hypotenuse squared. Combining these two terms that are alike, we'll learn a little more information. And then since we have a square on both sides, we can actually take the square root of both sides of this equation. Now, the square root of x and h, x squared and h squared will just be x and h. The square root of 2 does not have a perfect square, so I'll just leave that as the square root of 2. That's going to be an irrational number. So what that actually means for us is if we have the leg x, right, of any 45, 45, 90 triangle, to find the hypotenuse h, all we'll need to do is multiply it by the square root of 2. It means it's square root 2 times larger. Well, that also means that if we have h, we can divide by square root 2 because it's square root 2 times smaller. So what we have is kind of a shortcut of the Pythagorean theorem once we understand this relationship for any 45, 45, 90 triangle. Let me show you two examples here. So in the first one, we have a leg labeled as 2. And since it's isosceles, this other leg labeled b will also be a length of 2. And then rather than going through the Pythagorean theorem, you can conclude that the hypotenuse is exactly square root 2 times larger. So it would be your leg length 2 times the square root of 2. So if you wanted to get a decimal approximation, you open up a calculator. I'm going to take the square root of 2. I'm going to multiply it by 2 and get my answer there to be 2.828 rounded off to the nearest hundredth, 2.83. So I'm going to say that A is approximately 2.83. Likewise, let's take a look at the second example where you have a hypotenuse given. So in the second example, our hypotenuse is 26, but we don't have either leg length. They'll be the same. F and E will be the same. And to get it without using the Pythagorean theorem quickly, we just understand the relationship that I can take the hypotenuse and then this time divide by the square root of 2 to get either E or F. So if I were to grab my calculator for this, 26 divided by the square root of 2, I get 18.38 when I round that off. So I'm going to put approximately 18.38. So in the real world context, this would most likely be used if you wanted to avoid using the Pythagorean theorem and find a quick way to square things up. It could be used at construction. Here is not a real life example, but if you think about a baseball diamond in the standard professional league, the distance between any two bases is 90 feet. So here labeled we have from first to second base is 90 feet. We could also conclude that it would be 90 feet from home plate to first base. So that would mean if you were to find the distance across the diamond, so if the catcher were to throw, all the way to second base, for example, and you wanted to know how far that was, it would be nothing more than taking 90 and then multiplying that by the square root of 2 and figuring that out. And that can be used anywhere in any context where you have a 45, 45, 90.